All right, so we're going to start looking at chapter 2, okay, the first section, 2.1, and it's on angles and how we measure them. So two different ways that we can measure angles in trig, or the units we use. Degrees is one of them. Does anyone know the other unit you can use to measure angles besides degrees? Yeah? Radians. And radians is a more common way of measuring angles when you start to get into trigonometry, some things in calculus. So we're going to learn radians. So big thing by the end of today is how do you convert between radians and degrees? That's kind of what we want to figure out. So first I'm just going to start, before we even measure an angle, I'm just going to talk about, well, what is an angle? And an angle is basically made up of two rays. Kind of like this. Here's a ray. Here's another ray. And to make that an angle, you just have to have the two rays start at a common point called the vertex. There you go. And that's an angle. At least that's an angle that's not part of a shape. It's just an angle all by itself. So generally, when you draw an angle all by itself, you have two rays. When you draw an angle in a shape, that's a little different. So if you draw an angle like this, okay, there are three angles here, but these aren't rays. What are those?
Line segments.
Line segments, yeah. So when you draw an angle in a shape, it's usually where two line segments meet, but when you draw it all by itself, it's where the two rays meet. Any question on that? Okay. So the idea of what's a ray? Well, it goes in one direction forever. That's why it has an arrow pointing. I basically just said that to you guys. If you put two rays together with a common vertex, I kind of jumped ahead, you get an angle. There's another example of an angle. Yeah?
Degrees have that have a little circle thing above the number. What symbol do we have for these ray angles when we're doing it in the other form?
When we do radians, I'll show you. Yeah, I'll show you. It's not so much as what the symbol is, it's more lack of a symbol. Yeah, so you'll see. Yeah, so there's your angle. Now, technically, we can name the sides of this angle. Okay, this is called the initial side, and this is the terminal side. So how do you know which side is which? Well, the way you can figure it out is if you put yourself between the two rays, so in the interior of the angle. If you rotate counterclockwise, where you end is the terminal side. So put yourself between the two rays, rotate counterclockwise. Where you would end is the terminal, and where you would start is the initial. Here's another picture of the same kind of thing. If you took your angle and rotated it, that doesn't change anything. Right, so if we just group all that together and now rotate it, the initial side is the one that's pointing kind of up and to the right, and the terminal side is the one pointing up and to the left. Doesn't matter how it's rotated. I will tell you that normally there is a certain way we like to put the initial side. It's not like that. That's more typical. We usually put the initial side horizontal. But, I mean, you could do it like that. Okay. So any question on the initial side versus the terminal side? All right. So now let me show you something from a program on the computer. So what I want to take a look at is drawing an angle. And when you draw an angle, there's really two ways that you can kind of rotate when you start to draw it. So one way I could rotate is clockwise. All I can do in this program is move the terminal side. I can't move the initial. The initial side always stays horizontal. But the more that I rotate in this direction, the more positive the angle's getting. Until I get all the way around, and then I've gone around 360 degrees, or a certain amount of radians. We have to figure out how does that number come up? Why is it that number? And if I keep going, I just keep getting a more positive angle. Okay, the further around you rotate, the bigger that the angle gets. Now, if I go back to 0, what do you think would happen if I keep going in the clockwise direction? What kind of angle do you think I would get? Yeah, we can get a negative angle. So for the purpose of drawing an angle on a circle like that, a positive versus a negative angle just tells you the direction that you went to get to the terminal side. All right, so let's write that down. So if you rotate in a counterclockwise direction when you draw an angle, okay, if you go in a counterclockwise direction, that's a positive angle. Clockwise direction is a negative angle. Generally, when we talk about shapes like triangles, quadrilaterals, we don't talk about negative angles. Negative angles don't really make sense when you're talking about a shape. It only really makes sense when you need to talk about movement on a circle. That's what the negative is for. Just remember, counterclockwise, that's that way. So counter, opposite way the clock goes. Clockwise, that way. So any question on the difference between clockwise and counterclockwise? Generally, if we can choose what kind of angle we want to work with, positive. Positive is always an easier number to work with than a negative. All right, so I told you that earlier up here, when you draw an angle, we usually like to draw it so that the initial side is horizontal. Well, if you make the initial side horizontal, that's one of the things that you need to do to draw an angle in what's called the standard position. So for an angle to be in standard position, that means you drew it with its vertex at the origin. So you're going to have a set of axes. And you put the initial side not only horizontal, but on the positive x-axis. All the angles that you saw me draw in this program right here, these are all in standard position. The vertex always stays right where the axes cross, and the initial side always stays on the positive x-axis, right there. Terminal side can be anywhere you want. Depends what your angle is. So there's another angle in standard position. Okay, what if I take that angle and go like that? Is that still standard position?
No.
No, what's wrong?
It's not the origin.
The vertex is not at the origin. Okay. How about if I take this angle and turn it? I turned it a little too much for what I was trying to do, but something like that. Is that in standard position?
No.
No. What's wrong this time?
The initial side is not resting on the positive end of the x-axis.
Yeah, the initial side is in the wrong spot. Looks like the terminal side is on the y-axis. But the definition doesn't have anything to do with that. Okay, you've got to have the initial side on the positive x-axis. Just like that. Yeah.
So when you had it rotated up onto the y-axis, wouldn't that mean that the initial side was still on an axis, yes, but the degree of the thing was just above 180? Positive 180. It was just the turbulent side just goes so far the other way.
So are we talking about standard position?
Well, no, it's already out of standard position that
Yeah.
way, but couldn't have it just been that could still have been the initial side, but
So this is the initial side right here.
yeah. What if the initial side was the other side? Would it have just been a degree that's above 180?
When we talk about the initial and the terminal side, it's always with respect to you being like in the interior, not the exterior. Yeah.
Okay.
So you're right. Technically, there are two angles here. There's an interior angle, and then there's this exterior angle. But we're always going to refer to the interior.
Okay. So less than 180.
Right. When we're drawing, something like that, yeah, it would be less than 180. Yeah. And that's because most of the time when you start sketching like triangles and other shapes, we don't sketch angles that are bigger than 180 anyways in a triangle. All right. So any question on standard position? Okay. One more thing. Alright, there was one more thing I'm going to mention. We may end up mentioning this again at some point. But I want you to look at the difference between these two angles. And all I want you to do is focus on where the initial side and the terminal side are. Okay, so look at that. Look where the initial and the terminal side are. And now, look at that. How do the initial and terminal side now compare to where they were before?
Much further apart. Technically.
They're not in. What do you mean? So you're saying they're in different spots?
They're in the same spot on the circle, but the angle there.
Don't look at the angle.
Is
No, don't look
they're
at
in
the
the
angle.
same position.
Yeah, they're in the same spot. Okay, and then what if how would they compare now?
They're still in the same spot.
Still in the same spot. Okay, so there's a name for that. If two angles have the same initial and terminal sides, they are called coterminal. So let me write that down. Two angles with the same initial and terminal sides are coterminal. Now I want to look at the number, and I want to see what the difference is between the angle when they are coterminal. Okay, so 810 degrees is coterminal with 450, which is also coterminal with 90. So it might be easiest to think about the 90 and the 450. What's the difference between 90 and 450?
It's 360 apart.
They're exactly 360 degrees apart. So that's how you can find angles that are coterminal. If you take any angle, like 45, and you add 360 to it, you will find another angle where the terminal side is in exactly the same spot. Right? So let's write that down. So to find coterminal angles, you can add or subtract basically a revolution. That's what you're doing. You can add or subtract one full revolution. And the reason that comes in handy is because I told you earlier we generally like to work with positive angles. Well, you now have a way to take an angle that's not positive and fix it. Let's say I had, I don't know, negative 45. And I wanted to do something with negative 45. What can I add to that to make it a positive angle?
Positive 360.
Yeah, I can add 360. And what do you get if you add 360 to negative 45? 315. Yep. So negative 45 is exactly the same as 315. Why is that useful? Well, when we start to use trig functions on the calculator, let's say you had to take the sine of, let me just fix my calculator, and you'll learn more how to do this. Let's say you wanted to take the sine of negative 45. It's exactly the same as the sine of 315. Coterminal angles will have all the same answers on a calculator. So the goal is to try to find the easiest angle you can work with to get the answer, because they'll all be the same. Another problem that can happen is you could have an angle, try to get it on 55, like that, 1,755. Now, if you asked me what the sine of 1,755 is, I wouldn't know, because you've gone around too many times. It's hard to keep track of. But going around all those extra times wouldn't change the answer. That angle is coterminal with the other ones I just put in. Sine of 1,755. So if I was going to have to do that problem, I would subtract 360 from that as many times as I can to make it smaller, but not too many times where it becomes negative. So that's the idea of coterminal angles. Gives us an easier angle to work with that's not as big. And you still get the same answer. Okay. Any question on that idea? And I think we're going to mention coterminal angles again. We might do it tomorrow. It's just while I had that diagram up, it's handy to mention it right now. All right, degrees and radians. So now we're going to look at how do we convert between degrees and radians. Well, to convert between any two things, all you need to know is one true fact about them. Once you know one thing about them, you can convert anything you want. So let's look at something that's a little easier, like feet and inches. Can somebody give me something that's true about a number of feet and a number of inches? It can be anything that's true.
12 inches is a foot.
Okay, so 12 inches is 1 foot. Is that the only fact that's true? 12 feet inches?
24 inches is 2 feet.
24 inches is 2 feet, 48 inches is 4 feet. Any of those would have worked for what I'm about to do. I just needed something that was true. Now, let's say you gave me 80 inches. And you say, how many feet is that? Well, I'd say, all right, I got to know something that's true. That's my start point. In 12 inches, there's a foot. So in 80 inches, there's how many feet? So now I just have to solve my proportion by cross-multiplying. But the whole key was this. You had to already know something to start with. Okay? And that's what we're going to figure out here. What we're going to figure out is this. Once you know how many radians in 360 degrees, that's like knowing how many inches in a foot. It's a starting point that you can use to figure out anything else you want to know. Is it the only fact we could figure out? No. Just like in 1 foot equals 12 inches, it's not the only fact. But we'll start with that one and work from there. So first of all, if you didn't know how many degrees in a revolution, that's 360. Right? All right, so first thing I want to do is just kind of look at the word radians. And does that word kind of look like anything else? Yep.
Radius.
It kind of looks like radius. So what I'm going to do first is I'm not going to give you a formula to convert between degrees and radians. I'm going to give you a visual, okay, of what does a radian look like? Like how big is it if you draw it, right? So let's start with that diagram. Okay, so what I have there is a circle with an angle whose vertex is right at the center. From the vertex, I've drawn two rays coming out from the center. One of the rays hits the perimeter of the circle there, and the other ray hits the perimeter of the circle right there. I then connected the 2 points where the perimeter is hit by the rays to make that thing in red, which is called an arc. Okay, any question on the picture? All right, now, since this is a circle, what do you call the center to the edge?
Radius.
Radius. Not a radian, but a radius. So that's where we're going to start to see the connection now. So this is called the radius. And how about this distance up here?
And that also the radius.
That's also the radius, yeah. It's the same thing. Now, if you spread the initial and the terminal side apart just enough so that the length of that arc in red is exactly the same as the radius in black, then you've drawn a picture of one radian. Now, it doesn't always have to be this length in red is not always equal to that length in black. Because if I drew a circle and I drew my angle like this, and then my arc was just this little piece, does that piece in green look like it's the same as the length in red? No. You gotta spread the initial and terminal side just right in order to make the length of that arc exactly the same as the length of the radius. But if you do, you've just drawn a picture of one radian. And then, I mean, it's not perfect, but that's probably pretty to scale about what one radian would look like. So it's a little more than 45 degrees. You'll know exactly how much it is by the end of class. So the length of that arc in red is the same as the length of the radius in black. Then you have drawn a picture of exactly one radian. So it kind of gives you a visual of something you can imagine, what a radian looks like. It doesn't help you to convert between radians and degrees, but it gives you kind of a picture of one radian. Any question on that idea? All right, now, to figure out how many radians in a degree, we got to start with something, right? It's like, how do you, like, if you didn't know how many inches in a foot, how would you ever convert between inches and feet? Well, you can't. You got to have something to start with. Then you can build on that and figure out other things. So I'm going to give you a fact that we can build off of, and I'll explain what it means. It's not a very long fact, but it's important. And there's a few kind of key phrases here. If you measure an angle in radians, the it comes out the same as something else on the circle. It comes out the same as the length of the arc. But that only happens on a special circle called a unit circle. So first I'll explain what a unit circle is, and then I'll see if we can explain the rest of that statement. Okay, a unit circle is just a circle that has a special size. Does anybody know what the size would be of a unit circle? Anyone have a guess what the size might be?
When you say size, you mean like the diameter?
The radius, yeah.
Radius.
Usually we talk about it in terms of the radius.
1.
Yes. So a unit circle is just a circle with a radius of 1. Alright, so let's take a look at this diagram and see if we can kind of use it to make sense of this statement. So we're going to be looking at measuring two things. One thing we're going to measure is an angle. The other thing we're going to measure is the length of the arc. So let's go back to the diagram. The number at the bottom, that's the measure of the angle. Okay, that's measuring how big the angle is. The number over here at the end, don't worry about the whole formula. Just look at the number at the end, 0.77. That's measuring the length of the arc. How big is the angle in the picture now? 2.24. And how big is the length of the arc? 2.24. All right, let's do another one. How big is the angle now? The angle is 3.77. And the length of the arc is 3.77. So as long as you set your circle to a size of 1, the size of the angle and the size of the arc come out exactly the same. If your circle is not a 1, well, look at what happens now. The angle is 3.77. Is the length of the arc 3.77?
Yeah.
No, it's not a unit circle anymore. So this special fact, I'll never get it back. Oh, I got it. This fact only works on a unit circle. So how can we use that to figure out how many degrees in a full circle? Well, what we're going to do is, instead of figuring out how many radians in a full circle, what we can do instead is figure out the size of the arc that makes a full circle. Because if we can figure out this number, the size of the arc that makes a full circle, it's exactly the same as this number, which is the number we really want to know. So let's see if we can figure out the length of the arc that would take up a full circle. And that's going to be the same as this number. So when we have an arc that takes up a full circle, we really don't call it an arc anymore. What do you call an arc that's the whole circle? What's the name of that? An arc that's a full circle.
The circumference.
The circumference. So the idea is, if you can find the length of the circumference, that will tell you how many radians in a full circle, because the length of the circumference is going to be equal to the radians in a full circle. So now we need, what's the formula for circumference?
Diameter times pi.
Yep, so circumference, you can think of it as the diameter times pi, or you can think of it as doubling the radius times pi. Same thing. Okay. On a unit circle, what is our radius?
Radius is 1.
The radius is 1. What's 2 pi times 1? No, 2 pi. So 2 pi, that number that we just figured out, if we go back to our diagram, would be this number right here. The length of the arc is 2 pi. And that's the arc that goes all the way around the circle. So what would this number be? If the length of the arc is 2 pi, then this number would be, what is it? This would also be 2 pi. These two numbers are always the same in this kind of circle. And we just figured out this number. So we automatically know this number, which is what we really wanted. And I don't know if I can show you. I can't really show you going all the way around. Because once I go exactly all the way around, it resets to 0. But that's the idea. The length of the arc that goes around the circle is 2 pi. So that's how many radians go around the circle, 2 pi. Let's write that down. So now, instead of having a question mark there, we can say that there are 2 pi radians in 360 degrees. Okay, in fact, I'm going to put that right here. Now that's kind of like saying in 4 feet there's 48 inches. That's okay, but you could simplify that fact a little bit. What could you do to make that fact a little easier?
Divide by 2 on both sides.
Divide both sides by 2. Right, that's even better. So in 180 degrees, there are 3.14 radians. And I can show you that. Just I'll go back here. 180 degrees is how far around the circle?
Half.
Half. Let's go halfway around. Okay, that's as close as I can get it. And when I go halfway around, what number did I get for my arc length?
5.
Yeah, you got basically 3.14. I can't get it right exact. Yep, 180 degrees is equal to pi, or 3.14. Right, so that's better. But even better, when you give someone a conversion, what number do you usually put in the conversion to make it easy? Yeah? Usually you give someone a conversion with a 1, right? That's what Cam did. He said in 1 foot is 12 inches. He didn't say 10 feet is 120. Could have, but he said 1 foot is 12 inches. If you gave someone a conversion between like minutes and hours, you'd probably say 60 minutes in an hour. You could say 180 minutes in 3, but to be simple, you'd say 60 minutes in 1 hour. So what we want to do is take this and get a 1 in it. What side do you get a 1 on? Well, it doesn't really matter. Let's start by getting a 1 on the left side. How would you get a 1 on this side? What would you have to do to both sides of this equation?
Divide by 180.
Yes. Now it's still true. We didn't mess that up because we divided each side by the same thing. And what's 180 divided by 180?
1.
So we have 1 degree equals pi over 180 radians. So now you have a formula for 1 degree. If you wanted a formula for 2 degrees, what could you do on both sides now? Yeah, you could just multiply both sides by 2. Now you've got a formula for 2 degrees. Okay. What if you wanted a formula for 5 degrees?
Multiply by 5.
Multiply both sides by 5. What's in the red box isn't important. What's important is this. Anytime you're trying to convert from a degree to a radian, you take whatever you're trying to convert, doesn't matter what it is, and you multiply it by pi, and you divide by 180. Those are the 2 steps to convert from a degree to a radian. Multiply by pi, and divide by the 180. And what you put in the red box is whatever you want to convert. If you want to convert 12, then do 12 times pi, and then divide by 180. Now that's degrees to radians. Radians to degrees is the opposite. what do you think step 1 would be when you're converting the other way?
Multiply it by 180.
Yeah, so when we do it that way, let me just scroll down for a second, we're going to multiply by 180 instead of divide by 180. And what do you think step 2 would be?
Divide by pi.
Divide by pi. So these two things just switch when you convert it between degrees and radians. Now, because that's all that switches, they're kind of similar. They're easy to mix up. So I'm going to show you how you can remember which one is which. You just memorize it. That's one way. Or I could show you something else. So radians to degrees, multiply by 180, divide by pi. It's the exact opposite of what's above. All right. So how can you remember, which one is which? It's always either going to be this or this. Those are always the conversions that you use. Well, the way we can remember which one is which is you just have to remember two things. When I say degrees, I want you to think 180. So connect like those two thoughts, right? Degrees, 180. Degrees, 180. When I say radians, I want you to think pi. Radians, think pi. Degrees, think 180. If you can remember that, then all of this comes automatic. All right. Does everybody have the steps before we try some examples? All right, so let's try. So we've got 60 degrees, and we want to convert it to radians. Okay, so first thing I would do is this. Let's make it a fraction. Eventually, you might not have to do that. You can probably skip that step, but let's start with that step. Now, we're going to multiply this by one of two things. It's either going to be the 180 over the pi, or the pi over the 180. Look at the fraction that I already have. Where is the degrees in the fraction that I already have?
The numerator?
Yep, it's in the numerator. So you want degrees to cancel out. So think about where. You're all set with your pencil?
Yeah, sorry, it wasn't working.
So we got degrees in the top. We're trying to cancel it out so we can get radians. Where would degrees have to go in this fraction?
The denominator.
It would have to go in the bottom. That means radians is going to go in the top. Now we just have to remember which number I said to think of with radians and degrees. When you see radians, what number did I say to think of?
Pi.
Pi. And when you see degrees?
180.
180. So in this case, it's multiply by pi and divide by 180. Degrees cancels. And 60 and 180, that reduces. What number goes into both?
60.
Yeah, 60. There's lots, 2, 3, 5. Preferably the biggest one. So 60 goes in once. And how many times does 60 go into 180? 3. So what you're left with is 1 times pi divided by 1 times 3. And that's how you write the final answer. So how do you know whether that's degrees or radians? I said, well, it's not so much the symbol you use, it's what you don't use. When you do not put a label on it, it's automatically radians. That's how radians works. You usually don't see RAD. In fact, you never see that. I just did it on this first one to kind of help you with the canceling. But that's how you write the final answer. And I can show you the same thing on here. So if we go to 60 degrees, you'll notice for some fractions, it gives you, or some angles, it gives you a decimal. And then all of a sudden you get to certain ones, and it just changed. Oops. It changed to a fraction. Generally, angles that are multiples of 30 or 45, you're going to see them written as a fraction. Okay, some random angle, like 51, that's not a multiple of 30. They do a decimal. That's a pretty typical thing. Okay, there you go. 60 degrees is pi over 3. So now you know where that pi over 3 is coming from. Okay, any question on the first one? All right, let's try 150. And again, think of it as a fraction if you want. Where does degrees have to go?
Well,
Yep, it's going to go in the bottom to cancel out degrees in the top. And the number that you always associate with degrees? 180. And the other number that would go in the top? Pi, you got to get used to not writing RAV because you're not going to see it. So degrees is gone. Cross the zeros off if you want right away. And then what goes into 15 and 18? 3. 3 times 5 and 3 times 6. So your final answer, 5 times pi divided by 6. And that's 150 degrees in radians. Let's check it. So let's go to 150. And is that what we got? 5 pi over 6? Yep. Okay. Any question? All right, let's do one with a negative. Negative doesn't change how you do anything. Do it exactly the same way. So still converting from degrees to radians. Okay, what do you think is going to go in the bottom?
180 degrees.
180 degrees. And the top? Pi. What is the pi?
It's the radians.
It's radians. We don't write it. It's invisible, but that is pi radians. We will use 3.14 sometime. I think I have a problem where they ask you to round. I'll make one. Okay, so we'll do a round where we use the pi button. But for right now, we'll just keep this without a calculator. Okay, let's reduce. What goes into 45 and 180?
15.
Yeah, 15 does.
5.
5 does. Bigger is always better in this case. So what's a bigger number? 45. 45 goes into both. So 45 goes into 45 how many times?
1.
Goes in once. And 45 goes into 180?
4.
4. And what else can I cross out? I forgot to do it.
Alright,
Degrees.
Yeah, we cross out the degree symbol. So you're left with negative 1 pi. Usually we just write negative pi. Divided by 4. And because this angle came out negative, if you visualize it on a circle, it means you went which way?
Close.
You went clockwise, yes. Negative 45 degrees. And that's exactly what we got. Negative pi over 4. Okay, so any question converting degrees to radians and leaving it as an exact answer? These are exact. These are not approximate. Right, now let's do an approximate one. 107. That's not really a multiple of 30. It's not 45. It's nothing special. So we're just going to convert it, but we're going to use the calculator to get the decimal. How many? 2. I'll always tell you how many places to round to. If you ever don't see directions, just do 2. All right. So let's start with what's going to go in the bottom, because that's what cancels out. Okay, so what goes in the bottom? 180. And that's 180 degrees. And the top?
Pi radians.
Pi radians. Degrees cancels. Now, even if this reduced, I wouldn't do it, because you're just going to round it. So just type it in on the calculator, but always make sure you use the pi button. Why do you think I want you to use the pi button versus 3.14?
Just the 3.14 is rounded.
Yeah, the 3.14 is rounded. The pi button is a lot more accurate. I'll show you what happens if you use 3.14. Next problem, a later problem. Okay, so that's 1 point. If you round that properly, what do you get to 2 decimal places?
1.87.
1.87
Zero. Radians.
radians. Do I need to put the word RAD?
No.
Nope. By you not labeling that at all, it means it's radians. That's how they do radians.
How do you use the pi button on the calculator again?
Pi button, you press second and then the up arrow for the exponent.
Okay.
Yep. All right, so that's degrees to radians. Let's try a couple radians to degrees. Okay, I want you to get used to not seeing the word RAD. It's not going to be there in the homework or on the test. Pretend that next to pi, it says RAD. It's invisible. So RAD is in the top. Where would radians go in the next fraction to cancel out? Okay, so RAD is in the bottom. And what number is always with radians? Pi. Which means in the top we have 180 degrees. Okay, so RAD and RAD is invisible. That cancels out. So radians is gone. What else cancels out?
6.
So 6 goes into itself once,
And that goes into 30 times.
and 6 goes into 180 how many times?
30.
30. Anything else that cancels out?
The degrees.
No, the degrees doesn't, because radians,
So
radians and radians, and the pi cancel. So pi over 6 is equal to how many degrees?
30.
30. So if we go back here, I mean, I'm not going to check all of them, but if you go to 30 degrees, there you go, pi over 6. Now, if you can memorize what 30 is, then you can figure out other ones quicker. How does 60 compare to 30?
It just doubles.
It's doubled. So what's pi over 6 doubled?
Pi over 3.
Pi over 3, exactly. So if you can memorize like 30, then you could figure out any multiple of 30 quick in your head. Yeah, over time. You know.
So 90 would be pi over.
So 90 would be 30 tripled. So that's 30. What do you get if you triple pi over 6? Pi over 2. Yep, you get 3 pi over 6 when you triple it, and then that reduces to pi over 2. Yep, so 90 degrees is pi over 2. Okay, any questions on that one? All right, we'll do one more exact, and then we'll do a decimal. Now, this one you might be able to figure out based on what Cam just said. We just said 90 is pi over 2. Well, this is triple pi over 2. So how much do you think this one's going to come out to?
270.
Yep, that's 270. So when I do it in my head, I look at this and say, okay, I already know that. I have that memorized. Pi over 2 is 90, and it's triple 90, so it's 270. But if you don't have it memorized, you just work through it. Okay. When you are converting to degrees, what goes in the bottom? pi goes in the bottom. RAD is invisible. What goes in the top?
180
Degrees. Pi's cancel. And 2 goes into 180
90 times.
90 times. Now you're right back where I explained when we started. What's 90 times 3?
270.
There's your 270. Okay, any question on that?
What would 180 be?
180?
Yeah.
Well,
Oh, it
90
would
is-
be 2.
90 is pi over 2,
Yeah.
and 180 is double.
Yeah.
So what do you get if you double pi over 2?
Pi.
You just get pi. Yep. And if you go to 180, there you go. You get pi. Yep. All right. And let's do one with a decimal. So round to 2 decimal places. Now you should know what that is just by looking at it. It's 3 radians. But if you didn't, you could always look at the directions. And the directions are telling you convert from radians. So you know you're starting in radians. Okay? But there's no degree symbol there anyway. So you should know that that's a radian. Okay. All right. What goes in the bottom when we're converting to degrees?
Pi.
Pi radians in the bottom and the top.
180 degrees.
80 degrees. And this is going to be approximate, right? That's what that symbol means. It's not exact. So if you do 3 times 180, that gives you 540. And then you want to divide by the pi button. So that's 171.89 degrees.
So when you don't see the pi symbol above like if it's just giving you 3 radians and there's no pi symbol above it, then just multiply it to the 180 and divide by pi.
Yeah, the pi just doesn't cancel out.
Okay.
Usually when there is a pi symbol, when you write a radian, the pi symbol cancels out. When there's no pi symbol, it doesn't cancel out. Now, let's watch what happens if you would have divided by 3.14. 3 times 180, okay, there's your 540, and divide by 3.14. Rounded to 2 decimal places, is that the same as the answer we got?
No.
No, it's off quite a bit. 89 versus 97. So we don't want to use 3.14. It's gonna mess your answer up quite a bit. And then if you use that to say figure out something else, now it's going to be messed up even worse. So stick with the pi button.
How far would you have to go down pi to the calculator? Realize that you could just press the pi button. The calculator itself will just realize.
Well, the calculator only has, I think it only does 9 decimal places. It's just trying to get it to make more. Oh, now I've made the number too big, so it can't use decimal places. But if I put all those in and I hit enter, it's not going to retain all that. It only retained up to 857. So it's going to round after 1, 2, 3, 4, 5, 6, 7, 8. So the calculator is only accurate to 8 decimal places. So in order to use pi, you'd probably have to go a little bit beyond 8 decimal places. You know, if you went to like 10 decimal places, for most calculations, you'd probably be coming out with the same accuracy. So if you did 3.14159265358979323846264.
You missed 9.
I missed 9?
Yep. 7, 9, 3, 2, 3, 8, 4, 4, 6, 2, 6, 4.
It's pretty impressive.
So you can use however many, but just use the pi button and you'll be good. Yeah. All right. Is there any question on that? All right. So homework, again, remember it's in the new book. So make sure you go to the trig part. And it's 36 to 68 even. So there's some converting degrees to radians exact. some decimal, and then some radians to degrees, exact and decimal. So you will need a calculator, but you will not need a graphing one. In fact, for probably the first few weeks, we won't really need graphing calculators at all. Scientific. I mean, you can still use it, but you won't need it.